Today we're going to take a look at lesson 3.1, which is all about graphing polynomial functions. A lot of times people have seen this stuff before as far as like what a linear function looks like, what a parabola looks like, but this is going into a little more in-depth depending on specific pieces of the function. So the overall degree of the function, the leading coefficient, things like that. There's pieces of the function that are going to kind of clue you into what the graph is going to look like. So we're on page 131. Go ahead and kick off with example 1 here at the bottom of page 131. So classify polynomials. How can you write a polynomial in standard form and use it to identify the leading coefficient, the degree, and the number of terms? So they're looking for 3 things here. The leading coefficient, which is basically the number in front of the highest degree variable. The overall degree, they call it the degree, but it's the overall degree. So the highest degree that any of those terms have attached to it. And then the number of terms. Remember, terms are separated with addition and subtraction. So for example, 2x cubed, that is one single term because 2 is being multiplied by x cubed. That's one single term. But altogether in this polynomial, we have 3 terms because there's 3 things that are being added or subtracted, okay? So we're looking for those 3 things. One key thing that I'm noticing is back in that question, it says polynomial in standard form. This is not in standard form. So standard form polynomials basically say that the highest degree variable has to come first. Then the next highest degree variable, then the next highest, then the next highest. Let me kind of give you an example here. So something like 3x to the 4th plus 7x squared minus 4x plus 7. That is in standard form because the x to the 4th, that's the highest degree variable we have. That comes first. Then the next highest degree variable is x squared. Then the next highest degree variable is just x. Remember, that's x to the 1st, right? We just don't write x to the 1st. You just write x. And then technically the next highest degree variable is right here. Really 7 is 7x to the 0th. So that's the next highest degree variable. But again, x to the 0th, you're not going to write that. So it's just 3x to the 4th plus 7x squared minus 4x plus 7. That's in standard form. Highest degree variable first, then the next highest, all the way down to basically a constant or the least highest degree variable. Recall that a polynomial is a monomial, which basically means something that has one single term, or the sum of one or more monomials called terms. So for example, what we have here, this is a trinomial because there's 3 separate terms. If it was something just like, I don't know, 5x squared, that's considered a monomial because there's only one single term. There's not other things being added or subtracted to this. That's one term. The degree of a term with one variable is the exponent of that variable. So what they're saying here is you've got 3 terms with this given polynomial. Negative 4x is one term, 9 is the next, 2x cubed is the final. I know that because all 3 of these things are being separated by addition, so that means they're individual terms. So negative 4x, the overall degree is 1 because that's negative 4x to the 1st power. Remember, we're not going to write x to the 1st. It's just assumed that that's x to the 1st power. So the overall degree of that term is 1. This is technically 9x to the 0th power. So there's no variables at all here. So that's technically an overall degree of 0. And then 2x cubed, that variable has a degree of 3. So that's an overall degree of 3 for that term. So if this was going to be put in standard form, I would have to start off with the variable that has the highest degree. So it's 2x cubed. Then I'd go down to the variable with the next highest degree, which is negative 4x. And then I'd go all the way down to my constant, my number. Again, this is 9x to the 0th, so that's why that goes last, plus 9. So now we're in standard form, the highest degree variable first, then the next highest, all the way down to the least highest. Standard form of a polynomial, we already kind of just talked about that, so here's the standard form. They're saying a couple other vocab words here, leading coefficient. So remember, a coefficient is the number that's in front of the variable, right? So 3 is my coefficient here. 2 is my coefficient. -5 is my coefficient, right? It's just a number that's in front of that variable. So they're getting very specific here. They're calling this the leading coefficient. So basically what they want is the number that's all the way out in front of your highest degree variable. So in this trinomial, the highest degree variable is right here, the x cubed. So the number in front of x cubed is a 2. So that leading coefficient is a 2. The degree of the polynomial. Some people call this the overall degree. What you're looking for is the highest degree that any of your terms have. For example, this leading term, the highest degree is going to be up front if it's in standard form. That's x cubed. So the overall degree of this polynomial is going to be 3, because that's the highest degree you have. Example 2, understand end behavior and polynomial functions. They are giving you kind of an end-all rule happening here with all 4 of these examples, and we'll talk about all 4 of these examples here in just a second. How do the sign of the leading coefficient, so remember that's the number in front of your highest degree variable, and the overall degree of the polynomial affect the end behavior? Okay. So let me get my camera out a little bit so we can get all this on the same page here. Okay. All right. Notice this top left box, that's the odd degree. Then the top right box is the even degree, right? Bottom left is odd degree, bottom right is even degree. So there is a difference between these 2 degrees, odd and even, and these 2 right here. The difference is one's positive and one's negative. So if I have an odd degree function, so that's basically something like y equals mx plus b, right? Y equals 3x plus 7. X is to the first power. Let me go ahead and write this out. So if I'm looking at something like an odd degree, kind of like this example they're given here, it's going to be something like this. Y equals 3x minus 2. That's an odd degree because technically that's x to the first. Okay, 1's an odd number. Y equals 7x to the 5th plus 3x squared minus 4, right? Overall, yes, there's an x squared. That 2 is an even number, but you're looking at the overall, the highest degree that that function has. In this case, the highest degree out of all 3 of these terms, the highest degree is that x to the 5th. So because that 5 is an odd number, right, this is an odd degree function. So anything that has the highest degree, right, being an odd number, that's an odd degree. Something like an even degree would just kind of be what you're probably thinking, y equals x squared minus 4, right? The highest degree we have is x squared, 2 is an even number. These things can get really involved, like y equals 3x to the 6th plus 7x to the 5th minus 5x squared plus 4x. I mean, right, blah, 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 blah. Again, we don't really care how many terms are in this. You're looking for the highest degree term that you have here. Out of these 4 listed right here, the highest degree is right here, x to the 6th. 6 is an even number, so that would be an even function. Okay. Again, what's separating this top row from the bottom row is right underneath the odd and even degree. It says these are positive leading coefficients. These are negative leading coefficients. So with these examples that I just wrote out, right, we already said that this is an odd degree because the highest degree is an odd number. But where they're getting positive and negative is that coefficient, that leading coefficient out in front of that largest degree variable. So that's a positive 7. So this would be a positive odd degree. Let's make up some other ones. How about y equals negative 4x cubed plus 7x squared minus 3x plus 1, right? So out of these 4 options that they have here on this table, it can be an odd degree with a positive leading coefficient, even degree with a positive leading coefficient, odd degree with a negative leading coefficient, even degree with a negative leading coefficient. You're looking at 2 things here. You're looking at the highest degree variable you have here. This is in standard form, so the highest degree is right there. So it's an x cubed, so this is an odd degree function. And then that leading coefficient in front of that x cubed is a negative 4. So since it's negative, this will be an odd negative function. Y equals 5x to the 8th minus 7x to the 5th plus x minus 12, right? Again, you're looking through all these terms because it's not always going to be in standard form, so you don't always want to take that leading term. But if you look through here, that's x to the 8th, x to the 5th, x to the 1st. So the highest degree variable is right there. 8 is an even number, so this is an even function. And then that leading coefficient is a positive 5, so that's an even positive function. The interesting thing here is how they can classify every function out there as odd positive, odd negative, even negative, is because their end behavior is always going to look exactly the same. Let's look at an example here. So let's just look at this top left box. They've got 3 functions here. All 3 of them are odd degrees, and they all have positive leading coefficients. So look at this red function here. F of x equals x. That's an x to the 1st, right? That's the highest degree variable we have. 1 is an odd number, so that's why it's odd. And then that leading coefficient in front of x is technically a positive 1, so that's why it's a positive leading coefficient. Out of these 3 terms, the highest degree is x cubed, so this is an odd degree function, and then that leading coefficient in front of x cubed, that number is a positive 0.5. I don't really care what the value is, I just care that it's positive. And then this green function, the highest degree is x to the 5th, 5 is an odd number, the leading coefficient's a positive 2, so it's a positive function. What they're getting here though is what they're talking about up here in the vocab, this end behavior. Basically, you could have a function doing some weird stuff in the middle, right? But what are these end behaviors doing? The end pieces of the function, right? Are they going down and to the left, down and to the right? Is it going like this? Is it going up and to the left, down and to the right? That'll tell you what type of polynomial you're dealing with, just based off those end behaviors. If you look at this example here, these odd positive functions, look at the end behaviors. I wish I could mark on this. Look at the red function, right? It looks like this red function is going down and to the left, up and to the right. Look at the blue function. It looks like if I trace it left, it's going down and to the left. If I go right, it's going up and to the right. Same thing with the green function. If I trace it, it looks like it's going down and to the left. It's going up and to the right. So what they're trying to emphasize here is that every odd positive function that you encounter will always go down and to the left, up and to the right. It might do some weird stuff in the middle, right? You could have an odd positive function doing something like this, going up and down and up. That's an odd positive function. Another type of odd positive function could look like this, right? The end behavior is still the same. It's still going up and to the right. It's still going down and to the left. Sure, this stuff in the middle, it might look a little bit different. You might have something that looks like this, where it goes up super high, down low, you know. It might look different in the middle, whoops, sorry, but it's still gonna go up and to the right, down and to the left. So every odd positive function is gonna do that. Every even positive function is always gonna go, if you go left, it's gonna go up. If you go right, it's gonna go up. Notice on all three of these examples, the red, the blue, and the green, it doesn't matter what the function looks like. If it's an even positive function, it's always gonna go up and to the left, up and to the right. Look at the ones at the bottom. Every odd negative function is always gonna go up and to the left, down and to the right. Look at these examples. Look at the blue one. It's going up and to the left, down and to the right. Look at the green one, up and to the left, down and to the right. The only thing that's different with all three of these functions, since they're all odd negative functions, the end behavior is going to be the same. The only thing that's different is what's happening in the middle. How many twists and turns will happen? Okay. And then the last example, every even negative function is always going to go down and to the left, down and to the right. Okay. Just the stuff in the middle is going to look a little bit different. All right, example 3. Consider the polynomial function f of x. How can you use a table of values to identify key features and sketch a graph of the function? What they're really getting at here is just being given this table of values, you can tell if this function is increasing or decreasing in what they call using these turning points. Let me get a piece of paper here. So if I have a function like this, right? They're calling these things turning points. It's literally where your function is turning, where it's going up, 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 and then it stops going up. The slope becomes 0. It doesn't go up any further, but then it continues to go down, 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 right? So that's a turning point. This is a turning point. This is a turning point. So wherever your function is going in one direction and then turns to go the other direction, that's what they're calling a turning point. So using a table of values, right? If we had calculators in front of us, if we were in class, I would show you on a graphing calculator. You could also go to Desmos, right? Go to Desmos, type in that graph, that function, and you'll be able to see exactly where all these turning points are at. Let me emphasize that too. Please feel free, not a lot of people have graphing calculators at home, but you should be opening up Desmos when you're going through these problems, when you're doing practice problems, when you're doing test questions, right? Anytime you're doing any assignment or assessment, feel free to open up Desmos, type in that function, and look at the graph and see how it's behaving, where it's turning, right? Any maximums or minimums. We're going to talk about that here in a second. But you can get a lot of information just from getting a picture of that graph. So feel free to always open up Desmos and type that in, and you can see what's happening here. But what they're saying is make a table of values. Your x's can be anything. Those are your inputs. So you could have -20, -15. You could skip by numbers. They're just skipping by 1, just keeping them nice and even for you. But then your output is going to be dependent on your input. So your inputs can all be integers, nice even numbers, but your outputs, you could get decimals, you could get fractions, but that's okay. Don't worry about it. But what they're emphasizing here is as your x values increase, so if I have a graph, obviously -3 is over here, +3 is over here, right? So as I go from left to right, this is what my function's doing. So at -3, it's going to be at -11.5. At -2, it's going to be at 6. At -1, it's going to be at 4.5. So you can kind of see just based off of just generally plotting those points, they're not exact. you can see that this function comes up, hits that point, comes back around, right? So that is a turning point right there. 0, it's going to be at 2. And then at 1, it's going to be back up to 4.5. So it's going to turn back around right there. So just by picking random points on your graph and plugging them into your function to get the output, you can kind of get a picture of what this function is going to look like. Let me just be clear, how are they getting this table? They're wanting you to make one. So how you would make a table is you can pick any input, any x value you want. All you're going to do is plug that into your function. So what they're doing here, when they pick -3, they just picked that out of thin air. They went and plugged that into the function to get -11.5. So it's going to be f of -3 equals -0.5 times -3 to the 4th plus 3 times -3 squared plus 2. And when they did the math, they get that f of -3 equals -11.5. So that's how they're filling out the table. They're picking any random input, they're plugging it into the function, doing the math, and then that gives you the output. Once you do that, you'll have a table of values. You can plot them. You can plot them inside Desmos. You can just sketch a graph real quick just to get the overall general idea of how this function's behaving, what the end behavior's like, where the turning points are, kind of how it's changing from one point to the next. They have already got it here for you. So this is a polynomial with, so after you go through and you plot all those points, that's this red function right here. Here are all the points. You can see them plotted kind of in the background there. So what they're telling you is you have some minimums and maximums. There's different vocab words about these out in the, if you go search YouTube, you might hear different, they might call these different names, but they're just minimums and maximums. So basically if you have a function and it's going up, 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 and then it kind of makes a turn right there, that is a maximum. You're reaching a maximum value, a maximum y value right there, because then it's going to turn and come back down. So there's a maximum right there at that arc, right, that turn. Then right here, if you look at it, there's a minimum because it's going down, 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 down. It hits a point and then it bounces back up. So that's a minimum. That's the smallest y value you're going to reach at that area right there. Then it turns, it goes up, 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 hits a maximum, and then starts coming back down. So this has relative maximums right there and right there. It's got a relative minimum right there. So it's just wherever you're hitting maximum y values or minimum y values. And you're kind of focused on just that turn. You're not looking at the overall picture. At each turn, that's a maximum. That's a minimum. That's a maximum. How can you use the graph to estimate the average rate of change over the interval -2 to 0? So what they're saying is from -2 all the way to 0, what's that rate of change? What's that slope between those two x values? So it looks like you're going from about right there on that function to about right there. So going from there to there, how can you calculate that rate of change? Or slope, right? That's the same thing as slope. So you got a formula for that, right? You can take those values of those points at those two, at x equals -2 and at x equals 0, and you can plug them into your formula. You subtract your y's over in your numerator, and then you subtract your x's in the denominator. So they're just doing that right here. They're plugging in those values. So they're saying at 0, 2, that's one of those points right there. And then they're saying at -2, 6, that's the other point. So they're just plugging those in. Example 4, sketch the graph from a verbal description. How can you sketch a graph of the polynomial function f from a verbal description? F of x is positive over these intervals. It's negative over these intervals. It's decreasing, so it's going downhill over these intervals, and it's increasing, so it's going uphill over this interval, okay? So it's giving you some stipulations, some rules, some things that are happening with this function. And again, you're just sketching this graph. So if you look down here at step 4, there's the graph that they're wanting you to sketch. So let me see if I can zoom this back out. Okay. So up here in the instructions, kind of in the start, they're telling you some specific information that your function is positive, right? That it's above the x-axis. So up above the x-axis, that's a positive function. Down below the x-axis, that's a negative function. So it's positive over the intervals from -infinity to -4. So from -infinity, as far left as you can go, until you reach -4, that function is positive. It's above the x-axis. So that's where they're getting that part there. It's also positive from -1 to 4. So between those x values, -1 to 4, that's why they have it positive up above the x-axis between -1 and 4. Oops, sorry, I think I'm too far over. -1, there we go, -1 and 4. Between those two values, -1 and +4, notice that your function is above the x-axis. It's negative over the intervals -4 to -1. So from -4 to -1, that's negative. Notice it's below the x-axis. Same thing between 4 and infinity. So as soon as you go on from 4 all the way to infinity, all the way to the right, it should be negative. So this function is continuing to go down and to the right forever. It's going to be decreasing, which means it's going downhill between these intervals from -infinity to -2.67. So basically, 2 2/3. So from -infinity, which is all the way to the left, all the way until -2.67, which looks like it's going to be that dot right there. Notice that it's going downhill until -2.67. So at -2.67, that's that relative minimum, right? The function goes down, 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 down. You hit a minimum y value, and then it bounces back up. So it's decreasing there. And then from 2 to infinity, it's also decreasing. So from x equals 2 and then all the way to the right forever, that function will be going downhill. So it's all decreasing from x equals 2 forever. And then it's increasing over this singular interval from -2.67 to 2. So if you look, that's that -2.67 all the way to 2. Notice that it's going uphill, right? So that's increasing, it's going uphill. So that's how you kind of piece all this stuff together. Sometimes, I would recommend getting scratch paper, getting graph paper, kind of like what they're showing here. Sketch yourself an X and Y axis. Use a pencil because you might make a mistake and you might have to go back and sketch it out and, change it. But just start sketching it, right? They're telling you that it's positive over this interval. So just put yourself on a -4 and then you know that it's positive. Is it going up and to the right? Well, we don't know. I mean, just kind of sketch a line that's going positive. And then once you get the overall picture at the end, you'll be able to see exactly what's happening. But just kind of go through there one step at a time. Put in the pieces of information they're giving you. And at the very end, again, it's not going to be a pretty picture, but you're going to be able to tell what that function's looking like in general. Number 5. So interpret a polynomial model. In science class, Abby mixes a fixed amount of baking soda with different amounts of vinegar in a cap bottle by a balloon. She records the amount of time it takes the gases produced by the reaction to inflate the balloon. From her data, Abby created a function to model the situation for X quarter of cups of vinegar. So we don't really know how many quarter cups of vinegar. They're just saying X amount. It takes T of X, that function right there, seconds to inflate the balloon. So for every quarter cup of vinegar, it's going to take so many seconds to inflate the balloon. So I'm assuming the more vinegar you add, the faster it's going to inflate the balloon. How long would it take the balloon, take to inflate the balloon with 5 quarter cups of vinegar? So they're telling you to use technology. Again, if we were in school, I would have you take out the calculators, and you could do that with technology. But right now, you're not going to be able to, at least, with calculators. Don't forget, you have Desmos available to you. Go to Desmos, type in that function, t of x, and you'll be able to kind of read that graph.